All right, so first thing, my mic should be significantly better. I switched it out for the one that's usually connected to my desktop. But so today we're kind of speed running chapter 8. I really, it's just for my extra credit. I have to do 2 problems, but we are going to read this chapter. So let's just get into it because it's going to take a while. All right, so in this chapter we begin the study of a completely different type of model for the processes that evolve in time. Discrete dynamical systems, or difference equations. Unlike differential equations, these models are well suited to situations in which changes occur at specific times rather than continuously. For example, we often measure population growth at specific times, such as the year end of a reproductive cycle. The study of discrete dynamical systems most often involves the process of iteration. To iterate means to repeat a procedure numerous times. In discrete dynamics, the process that is repeated is the application of a mathematical function. We have encountered several types of iterative processes already. For example, Euler's method. As was the case with differential equations, we see that finding an exact solution of discrete systems is rarely possible. As usual, we rely on a combination of numerical, analytic, and graphical techniques to understand these systems. Even with these sophisticated techniques, we are unable to describe even one-dimensional nonlinear iterations completely. The reason is that many discrete nonlinear systems behave in a complex and unpredictable manner. This phenomenon, called chaos by mathematicians, is discussed at length in 8.4 and 5. Okay, so 8.1. Let's just take some notes and then we'll... All right. The discrete logistic equation. The population models we have studied so far all have the property that the rate of change of the population is continuous. This is a reasonable assumption for species that reproduce quickly with respect to the time scale we are considering. However, for some species, all births occur in the spring and most deaths occur during the winter. Hence, the assumption of continuous population change is not valid. Instead, we should think of time as discrete. If we measure the population once a summer, then we will have an accurate estimate of the population for the entire year. We begin our study of discrete time systems by recasting several of the population models we discussed in Chapter 1 as discrete dynamical systems. Okay. The exponential growth model. The exponential growth model is a simple but unrealistic model of population growth. We discuss it at first because it illustrates the main idea behind discrete dynamics. In this model, we assume that the population of a certain species is in the next generation is directly proportional to the population in the current generation. We let P of n denote the population. Okay, so this is all pretty simple, right? Unlike the differential equation, which tells us the rate of change of the population, this differential equation tells us directly the population of P of n plus 1. Okay, so then we get this formula, k to the n p 0. So we see that the population at generation n is determined by the formula p of n equals k to the n p 0. Therefore, if p 0 is greater than 0, we conclude that if k is greater than 1, the population explodes. Right, we did this in linear algebra. It's like there's this fundamental difference between what 0 and 1 means. 1 is kind of the discrete version of 0 in a way. Because, okay, the logistic difference equation. To make the exponential growth model somewhat more realistic, we add assumptions that account for overcrowding, just like we did in the differential equation. The population at the end of the next generation is proportional to the population at the end of the current generation, when the population is very small. If the population is too large, then all the resources will be used and the entire population will die out in the next generation and extinction will result. The last assumption is slightly different from the one we made in the differential equation. Here we assume there is a maximum population level M that when reached results in extinction of the population in the next generation. Thus, M is called the annihilation parameter. If the population ever reaches M, the species is doomed. Right, and it doesn't even make sense if P of N is greater than M, because then you have a negative population. As before, P of N denotes the population at the end of the generation N, and P0 is the initial population. If P of N is small, then the term is approximately 1, so the difference equation is almost the proportional growth, the exponential growth model. On the other hand, if P of N is greater than M, then P of N plus 1 is less than or equal to 0. That is, the population is non-positive. We interpret this to mean that the species is extinct. Rather than deal with the large numbers that often arise in population models, we assume that P of N represents the percentage or fraction of this maximum population alive at generation N. We assume M equals 1 and P of N lies between 0 and 1. We call it the discrete logistic equation. Okay, so we're going to write down P of N plus 1 is equal to K times P of N. Then this goes into K, P of N plus 1 is equal to K P N times 1 minus P N over M. Then we say M equals 1 and treat P as a percentage. And we get the discrete logistic equation, which is P of N plus 1 is equal to K P N 1 minus P of N. Discrete logistic eq. Wait, actually, you know what we should do? Because I don't necessarily want to spend too long on this. I'd rather do quiz prep because this is not going to be on the quiz. So let's just scan maybe. For the discrete logistic model, finding successive populations is the same as iterating a quadratic formula of the the list of numbers is called the orbit. Okay, so a trajectory is called orbit. And fixed points and equilibrium points are called fixed points. This orbit is eventually fixed since and then okay, so then there's also eventually fixed points. Consider how do they write it? They say consider orbit of minus 1 under f of x equal to x squared. Because then we go from minus 1 to 1 to 1 dot dot dot. Okay, great. For any other c, there now consider x0 equals 1/2, then xn equals 1 divided by 2 to the 2 to the n. Cycles. In a typical discrete dynamical system, there are often different types of orbits. For example, the orbit, okay, so then we say like example of cycles, so cycles, g of x is equal to x squared minus 1. Orbit of 0, it goes 0 to minus 1 to 0, dot, dot, dot. So we say cycle of period 2. That makes sense. And then there's also minus square root 2 is eventually periodic. Because we go from, oh wait, not minus root 2, what am I talking about? You go from root 2 to 0, oh, to 1. Oh yeah, to 1, to 0, to minus 1, and to 0, dot, dot, dot. Okay. In contrast, if we take 1/2, tends to the cycle of period 2. So that's interesting. Take 0.5, it tends to the cycle of period 2. That's really cool. It's important to realize that this orbit actually never reaches the cycle at 0 and minus 1. Rather, the orbit becomes arbitrarily close to these two numbers because of round-off error. Oh, one thing I want to do, actually... Oh, no, never mind. Okay. Okay. Thus, the orbit is not eventually periodic. So 0.5 not eventually periodic. So it's technically different from an actually eventually periodic thing. Though in practice, the fate is basically the same. Yeah, but it's still interesting, you know. But the fact that things that converge to periodic is like really cool. Okay, discrete dynamical systems may have orbits that cycle with any period. Okay, we can construct discrete system with arbitrary length period. I would love to dig into this more, but we really have to we're gonna get into the logistic map, bro. It's gonna, okay. How far into this chapter do we think the bifurcation plot shows up? Surely it shows up. Dude, I want to get into this chapter. Maybe we'll do it later this summer when I have more time. Come on, where's the bifurcation plot? All right, so we got this. Come on, we're leading up to it, baby. Come on, how can you have a chapter on discrete dynamical systems and not show? It's going to be in chaos. Bro, really? It's not in this? I feel like if you look up bifurcation diagram, yeah, you get the logistic map bifurcation. I'm so surprised that this plot is not in my book. That's kind of nuts. Oh, well, they have a lab on it. Oh, and they get you started. That's cool. All right, let's go back. All right, so here we go. Time series and histograms. One convenient method to describe orbits geometrically is via time series. In these diagrams, we plot the iteration count on the horizontal axis, and then the numerical values of the orbit on the vertical axis. It often helps to draw straight lines connecting successive points in the time series. Okay, we plot the time series of minus 0.5. Okay, see this? So it converges to that period 2 orbit. Okay, in 8.2, we plot the time series of 0 on this. We see that the orbit tends to a cycle of period 4. That's interesting. Eight point 3 displays the time series for the orbit of 0.5 under the iteration of the logistic function with 3.9 as the growth. This is neither fixed nor periodic behavior. It is difficult to see any sort of coherent pattern. So they kind of have this is basically one slice. We study this sort of time series in 8.5. Another visual way of displaying orbits is a histogram. Okay, so we can visualize orbits as time series or histogram. These images subdivide an interval that contains the points of an orbit into many sub-intervals of equal length. Each time the orbit enters one of these sub-intervals, okay, I know what a histogram is. Okay, the histogram for the orbit of 0.123 under the logistic at this. So this thing, though, really has a period 3, or at least it's almost a period 3. So yeah, I can see why the histogram is useful. In the first case, wait. What? Figures 4 and 5. Okay, so this is 4 and this is 5. Okay, so we're changing the parameter just slightly. In the first case, the orbit quickly settles down on a period 3 cycle. In the second case, we see a different view. The orbit apparently never settles down, instead visiting all of the subintervals, but some more than others. Dude, that's crazy, bro. I love chaos. It's just so insane that this happens. And all you do is tweak this number just a tiny, tiny bit. All right, finding fixed points. Finding fixed points. As we see from the examples above, there are many different types of orbits for a discrete dynamical system. Fixed points are the simplest, and these are often the most important types of orbits in such a system. As in the case of differential equations, we use 3 different methods to find these orbits: analytic, qualitative, and numerical. The analytic method involves solving equations. Given a function f, find the fixed point for f. We need only to solve the equation f of x equals x. Okay, so when we have the analytic solve f of x equal to x. Okay, cool. Right. Oh, this is fun. Geometrically, we can view fixed points as superimposing the graph of x, y equals x, and the graph of the function f. Note that the diagonal meets the graph. Yeah. Okay. So geometrically, plot y equals x and y equals f of x, and c. Okay, so here's another one. So we have 3 fixed points of this thing. Okay, that's fun. Okay, here we find the fixed points for the logistic equation. Recall that our population model, we assume x is between 0 and 1. So the second fixed point is positive only if k is greater than 1. When k is less than 1, this fixed point is negative, and so it's not biologically interesting. Also, k minus 1 over k is less than 1 for all k greater than 1. The fixed point x equals 0 represents population extinction, and the non-zero fixed point represents population that never changes from generation to generation. Figure 8.8 shows the graph for k equals 4. So if you had population 1 of, it would be 0. So what's crazy is that if you're here, then you instantly go to there, right? Given f, finding the fixed points by solving algebraically may be difficult or impossible. If we need a more accurate, we get from graphical methods, we can turn to numerical methods. We can use Newton's method. Okay, notation for iteration. Notation. F to the n of x equals f of f of f dot 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 of f, n times of x. Wait. Oh, okay. Yeah, means, okay, that's fine. Finding cycles. Hey, what's up? Differential equations and dynamical systems. Okay, finding cycles. To find cycles for a discrete dynamical system, we proceed in essentially the same manner as for fixed points. Okay. Wait, what? For example, if h equals minus x cubed, the only fixed point of h is 0, since the equation for the fixed point equal to x only has, right, well, for a real, you have complex solutions. For the cycles period 2, we must compute, oh, interesting, okay, so to find cycles of period n, you take h to the n of x equal to x. Okay, that's cool. That's actually so cool, man. Fixed points are just periodic solutions of period 0. That's a nice way to put it. The solutions here are the fixed point x equals 0. You guys can probably hear that noise. I turned off my noise filter because I think it might be causing some weird sounds. Finding cycles is usually more difficult than finding fixed points. Yeah, that makes sense just because your expressions blow up. Because then we have to find the roots of a 4th degree. Okay, luckily we know 2 solutions from this equation already. Okay. The quadratic equation has roots minus 1 plus or minus square root of 5 over 2. These points lie on a cycle of period 2. Okay. Okay, yeah. So in general, you just... But finding periods gets crazy because... all right. Finding cycles geometrically. Now that's interesting. Oh yeah, you can just plot... Right, you can also do geometrically by plotting y equals x and y equals h to the n of x. Easy, bro. And then you can find the cycles of period 2 visually. I love the geometric approaches. Yeah, look at that. That's beautiful. Okay. All right, so we're actually not, as much as I would love to do the exercises, we just do not have time. We just got to keep reading. All right, so now we're going on to, so this is 8.1. This is DE 8.2. All right, so there are a couple of exercises I think there's one exercise. Let's see what it is. It's number 30. So we're going to read all this. We are going to read it. But it's problem 30. Recall from calculus that Newton's method is an iterative procedure to find the roots of a given function p. dp dx. Show that a root x of p for which x prime is not equal to 0. Wait, hold on. Show that... How's my volume from here? Is my volume good from here? Where do you find these notes? I need to study. So this is just a book, dude. It's in the title of the video. Differential equations Blanchard. Okay. Show that a root x of p. So this is going to be 0. But this is non-zero. So what's an example where p of x... Okay, let's make the polynomial like x minus 1. If we have like p of x equals x minus 1, then x equal to 1 is a fixed point, but then p prime is going to be equal to 1. So then, okay, so that's this problem is easy. So clearly it's a fixed point. Oh wait, is it a fixed point? Because this term goes to 0, so then it's going to be whatever it is. So if we gave it 1, then it's going to be 1, and then bam. So then the update procedure just stops. All right. Suppose p of x is equal to x cubed minus x. Determine whether the fixed points for the corresponding Newton iteration are attracting or repelling. So I don't know that one. So we're going to have to read the section for that. Okay, let's go to 8.310 just to see what the problem is, just to get our mind ready. For the logistic family, show explicitly there exists a cycle of period 2 for k greater than 3. Okay, so I don't actually know really how to do that. So we're going to have to read 8.2 and 8.3, and then we'll write up our solutions, and then we'll be done with this chapter, which is super interesting. This chapter is like, I really love this stuff, but we only have so much time. Cool. I'm glad, yeah. And I found the book online for free, so, don't tell anyone. All right, I'll be back in a second, and we'll get into 8.2. Okay, fixed points. Wait, actually, you know what? I'm gonna turn the gain down slightly because it does seem like I'm clipping. Okay, 8.2, fixed points and periodic points. As was the case with equilibrium points for differential equations, fixed points and cycles for difference equations come in several distinct varieties, depending on what happens to nearby orbits. Interesting, okay. In this section, we discuss analytic and qualitative methods for distinguishing different types of fixed points and cycles. Graphical iteration. As we saw in the previous section, the graph of a function and the diagonal line gave us a geometric method for finding fixed points and cycles. I really like that graphical approach. In this section, we see that the graph of f together with the diagonal line also provides a convenient way to sketch other orbits geometrically. Okay, graphical iteration. Given the function f and a seed x0, we view the orbit of x0 as follows. We begin at the point x0, x0 on the diagonal. Then we draw a vertical line from x0, x0 to the graph of f. So we reach the graph at x0, x1. Okay, so let me just do this. So we go x0, x0. Then we go to x0, f of x0. Now we draw a horizontal line from this point back to the diagonal. Okay, so then we go to x1, x1. Along this line, the y values remain constant. Excuse me. So we reach the diagonal at because this is very interesting. Yeah, that works. Because you're going to be at x1 here. And then if you go to where x1 is at x, then that point is going to be f of x1. Okay. Continuing in this manner, the orbit of x0 is displayed as a sequence of points along the diagonal. The resulting picture, which sometimes resembles a staircase, sometimes a cobweb, is called a web diagram. Okay, web diagram. The process of drawing the vertical lines is called graphical analysis or graphical iteration. We sometimes add arrows. That's fun. This is super cool. Oh, I really like this. Let's look at this one. So this is our seed. So this part's interesting, right? It's like that's so weird, man. Okay, cool. I like this a lot. We clearly see two fixed points for G. Oh, because this intersects here. Yeah, okay. Given by the points where the graph crosses the diagonal. Note that the orbit of x0 equal to 1.4 tends away from one of these fixed points and toward the other fixed point. Ah, yes. Another important type of orbit for discrete systems is the cycle or periodic orbit. Recall that for a function f, the seed x0 lies on a cycle or periodic orbit of period n. Yeah, so this is just the definition. Remember that this is the iterate, not the power. Equivalently, x0 lies on a cycle of period n if the orbit of x0 is a repeating sequence. Graphical iteration allows us to visualize cycles without having to compute the graph of f to the n. Ah, okay. For example, 0 and 1 lie on a cycle of period 2 for x squared minus 1. Since f of 0 equals minus 1, f of minus 1 equals 0, we see that this, so we're at minus 1 and 0. And an orbit tending to the 2 cycle. Oh, so that's interesting. So this approaches the 2 cycle. So maybe it's like, because the cool thing about equilibrium points and stuff like that was that we got these lines that in the phase portrait were the equilibrium solutions, and in between those lines, all the behavior was the same. So you had these pockets where everything was the same, and the boundary was just basically the equilibrium points. Here, I wonder if you can't, that you can't cross out of this. As we saw in the previous section, the logistic difference equation admits cycles of many periods. So this is going to be 1, 2, 3. This is period 3. This is a 4 cycle. 1, 2, 3, 4. Nice. Okay, this part we need to know. Attracting and repelling. Figures 18 and 19 display the graphical analysis of 2 additional logistic functions. In the first case, observe that the displayed orbit tends to a fixed point. But when the parameter is changed to 3.2, this is no longer the case. The displayed orbit comes close to the fixed point, but then tends toward a 2 cycle. This is an example of a bifurcation, a topic we discuss later. For now, note that there's a dramatic difference between the behavior of orbits but it depends on what the seed is, right? This is an example of a bifurcation, a topic we discuss later. For now, note that there's a dramatic difference between the behavior of orbits near the non-zero fixed point in these two cases. In the first case, the orbit is attracted to the non-zero fixed point, whereas in the second, the orbit seems to be repelled away. Oh, wow. Dude, that's crazy. Just as with equilibrium points for differential equation, there are different types of fixed points. All right, definition. A fixed point, x0, is called attracting if there is an interval around x0 having the property that every seed in this interval has an orbit that remains in the interval. Ah, bro, that's beautiful. Okay, so the definition of, attracting fixed point, FP. X0 of type fixed point is attracting if there exists an interval in which every seed in the interval has an orbit that one stays in the interval and two tends to x0. Now, repelling is if there's an interval around x0 having the property that every seed in the interval has an orbit that leaves the interval. What does this mean? A fixed point that is neither... Okay, so repelling means that every point that there exists an interval that every point leaves neutral fixed point around x0 is neither attracting or repelling. Attracting fixed points are the analogs of sinks. And what's a neutral? I want to see a neutral, though. A neutral fixed point is going to be one that has, in which there's no interval where every point leaves, and there's no interval where every point stays and tends. Stays and tends. I don't know what that looks like, though. All right, attracting fixed points of the analogs. Okay, so we looked at this picture. Fixed points of linear functions. To see what makes certain fixed points attracting and others repelling, we first consider linear functions. x0 equal to 0 is always a fixed point. Graphical analysis shows us that as long as the absolute value of m is less than 0, x0 attracts all orbits. Okay, so this is good. So, linear functions. Consider f of x equal to mx if abs val of m is less than 1, then x 0 equal to 0 attracts everything. Attracts all orbits. If minus 1 is greater or less than m, which is less than 0, orbits tend to 0 but hop around. Hop around. Right. When they're greater than 1, though, okay, when f is a nonlinear function, a similar story holds true at least near fixed points. If f has a fixed point x0 and f prime, and the absolute value of f prime of x0 is less than 1. What does this mean? This means that the slope of f at x0 is less than 1. Then the graph of f is tangent to a straight line whose slope is less than 1 in absolute value. As in the case of linear functions, then we have an attracting fixed point. Thus, a fixed point x0 for f for which, okay, so then we have for nonlinear f, look at absolute value of f prime of x0 less than 1. Note that this result is only true close to, right. All right. Fixed points of the logistic function. Consider L of 2.8. The fixed points for L are given by solving this. Some algebra shows that these are the fixed points. Now, okay, L prime. So L prime of 0 equals 2.8. What does that mean? That means that it's going to be repelling. Yep. Okay. As a second example, suppose we consider instead the logistic function with 3.2, and we solve, and we find 0 and 0.6875. Again, but now both of them are repelling. How do you prove it's repelling? You just show that because you have to show that every point leaves, that for every interval, that there's no interval in which every point stays in it. pretty cool. Okay, so now that we do the general logistic equation, and we find L prime of 0 equals K. So when K is greater than 1, okay, so then we do L of K of X, L of X is equal to Kx 1 minus X. L prime is equal to K minus 2Kx. So X equal to 0, it has L prime equal to K. And K minus 1 over K is attracting for minus 1 to minus K plus 2 minus K plus 2 less than 1. So 1 less than K less than 3. Here we go, neutral fixed points. That's what I was looking for. What are you studying this math for? What major am I? I am, funny enough, bro, I'm actually an art history major. I just love art history. I'm a dance major. That's funny. That's good. Yeah, I'm a dance major, bro. Examples of neutral fixed points. Neutral fixed points can occur only if oh, interesting. Okay, so wait, this is a DE section 8.2. Neutral fixed points happen when f prime of x0 is equal to plus or minus 1. Orbits near neutral fixed points may behave in a variety of ways. For example, consider minus x plus 4. F of 2 equals 2. F prime of 2 equals minus 1. All other seeds have orbits that lie on cycles of period 2. Hold on. Wait, hold on. Okay, wait. So 2... Okay, 2 goes to 2. So that's a fixed point. All right, so we know that... Okay, so if you take f of x equal to minus x plus 4. Then we can solve for x is equal to minus x plus 4. And we get 2x equals 4. So then x equal to 2 is a fixed point. Now we can analyze f prime of x is equal to minus 1, no matter what. Okay, now let's just look at the orbit of something else. Let's look at the orbit of, like, 1. Or what did they do? They did the orbit of... They didn't actually do another orbit. All other seeds have orbits that lie on cycles of period 2. Since, oh, see, okay, so this is what we needed to do. F2 of x is equal to This is actually crazy. Yeah, it's going to be minus x plus 4 plus 4. And if we solve for that, it's just going to be equal to x. So all points have period. All other points have period too. That's really, dude, I could see how you could go hard looking into this stuff, because this is really interesting. You can probably find all sorts of fun behavior. As another example, x plus x squared has a fixed point at x equals... So wait. Wait. What are they really saying here is the question, though. Okay, so those cycles of period 2, they're not repelling, and they're not attracting. Because even though they stay in their interval, they don't tend. So neutral fixed points, are they always periodic, though? As another example, okay, now consider g of x equals x plus x squared. All right, we have 0, and then this is equal to x times x plus 1. We have 0 and minus 1. And then g prime is going to be equal to 1 plus x. The graph of g shows that 0 attracts... Oh, crazy, dude. Crazy. Okay, so it's not just periodic. Wow. Damn, that's nuts, dude. So what do we see? So wait, how do we see that it's a neutral fixed point? Okay, we don't actually see that it has this behavior except for plotting some of the orbits, but we get. Hold on, I'll be back in a second. Okay, so I'm spending too much time on this because we just need to finish this. Because the problems don't even include all this stuff. All right. Classification of periodic points. Periodic points can be classified as attracting, repelling, and neutral. Oh wait. What is a periodic point? Do they define periodic point? I guess periodic points are just points that are in a cycle. If x0 lies on an end cycle, then the graph of f of n meets the diagonal. That is, f of n is a fixed point. Oh, that's a crazy way to think about it. Yeah, Fn, dude, that's a crazy way to think about that. Whoa. That's kind of mind-blowing. I mean, the whole idea of fixed points as zero cycles makes this cool. But so, if x0 on f is in an n cycle, then f to the n of x0 is equal to x0. Therefore, x0 is a fixed point of the function f to the n, which is not power its iteration. So f iterated n times. So it is natural to call this cycle, wait, hold on. It is not, what? Oh. So it is natural to call the cycle attracting, repelling, or neutral depending on whether the fixed point, okay, so then you call the cycle attract, repel, neutral if x0 on f to the n is attract, repel, neutral. That's so interesting, man. I feel like this type of stuff appeals to me, man. Like, I really enjoy that kind of thing. The function f has a 2 cycle at 0 and minus 1. Okay, so let's consider f of x equal to x squared minus 1. So then at 0 and 1, minus 1, we get 2 cycle. Now so since we have a 2 cycle, we take f, I don't want to say squared, f to the 2, which is equal to x squared minus 1 squared minus 1. So then we get x to the 4th minus 2x squared. Then we take this to d, we derivative, and we get x cubed minus 4x, right? Oh, wait. 4x cubed minus 4x. So then we plug in, so this is going to be f prime is equal to, or f to the 2 prime. So f2 prime of 0 is equal to 0, which means it's attracting. So it's less than 1, and attracting. Hey guys, how is my mic quality? I've switched up my mic quality, and I want to know if it's improved. It should be much better, but I'll have to do my comparison myself. There's only one person here. Okay, then we look at, okay, so then minus 1 is also an attracting. So what does that mean that so that a cycle is attracting, but you can probably have like you could probably have a neutral cycle. So then you can have, okay, so an attracting cycle Or wait, hold on. So you can have a neutral cycle that attracts from one side of the cycle and repels from the other. I'm predicting that we're going to have an example like that. So we can have this is my guess. This is my guess. We can have a neutral cycle that isn't just everything around it periodic, because we should do this for minus x plus 4. Minus x plus 4 is a 2 cycle. Okay, so where was our minus x plus 4? This. Okay, so if we can have a neutral cycle that attracts from one side and repels from the other. But what I want to know is what this tells us about the periodic point one. Okay, so we have f of x is equal to minus x plus 4, and f prime of x is equal to minus 1. Now, if we just do the orbit of minus 1, we get, of 1, we go 1 goes to 3, which is going to go to 1, which goes to 3. Okay, so we have our 2 cycle. And now that we have a 2 cycle, we want to classify this cycle. So we found it. Now we're going to take f2 of x, which is going to be equal to minus x plus 4, which when we simplify it all out is just going to be x. So then f2 prime is equal to 1. So it actually didn't tell us. Oh no, it did tell us. It told us that that's a neutral cycle. But I'm guessing you can have way cooler ones, like okay, like in here, where was one of those cool boxy ones? Okay, like in here, see this one, it attracts from the inside, but like I imagine that we can construct a function that repels from the outside, but on the inside it attracts. Wait. Yeah, the cycle is attracting from the inside and repelling from the outside. Okay, so where are we with this whole thing? Are we almost done? We gotta hurry this up, man. I could spend all day doing this. Classification of periodic points, we did this. Wait, hold on. Oh, okay, so we're back to here. The fact that f2 prime of x0 is the same at both points on the cycle in this example is no accident. The chain rule tells us why. Suppose x0 and x1 lie on a 2 cycle for f. Okay, so chain rule says, suppose x0, x1 are cycle points of f. So x0 to x1 to x0. Then f2 prime of x0 is going to be equal to f prime of f of x0 times f prime of x0, which is equal to f prime of x1 times f prime of x0. That is, the derivative of f2 at x0 is just the product of the derivatives along the orbit. This is true for this is true for any period. True for any period. So if we have f to the n prime of x0, but it has to be on a wait. Does it have to be on a cycle? Well, we at least have to know the order, or the orbit. I guess it has to be. True for any period. So x0 to xn minus 1 is equal to the product of f prime of x n minus I. Okay. All right, cool. So let's do problem 30, right? Okay, so we have xn plus 1 is equal to xn of p minus p of xn divided by p prime of xn. A, show that if show that if x is a root, so we're doing problem 30. If x is a root of p and p prime of x is not equal to 0, show that a root x of p for which p prime Dude, actually I love this. Because, like, they didn't really talk about involving derivatives in it, but it's like, Newton's method is so cool. Then x is a fixed point for f of x well, I guess f sub p of x is equal to x minus p of x over p prime of x. So that's kind of okay, and then the easiest way to show that is that if x root of p, then xn plus 1 equals xn minus 0 over non-zero. Okay, then part B, suppose p of x, so p of x is equal to x cubed minus x, equal to x times x squared minus 1, which is equal to x times x plus 1, x minus 1. All right, we factored it. Determine whether the fixed points for the corresponding Newton iteration. Okay, so what we need to do is say, so p prime of x is equal to 3x squared minus 1. So now our corresponding Newton iteration is going to be x minus x cubed minus 1 over 3x squared minus 1. And then since we're trying to find for the fixed points, we set that equal to x. And then we're going to end up oh wait, but then to figure out, so we need to find the fixed points, then we take the derivative and evaluate the derivative at those points, and then we can determine whether or not those fixed points are attracting or repelling. That makes sense. Okay, so x cubed minus 1 all right, so I forgot my long division. Oh wait, x cubed minus x. So we're going to get x over 3 minus 2/3 x divided by 3x squared minus 1 is equal to 0 because the x's cancel. So we get x over 3 is equal to 2/3 x divided by 3x squared minus 1. So what we could do is we could just multiply this instead. So we get x over 3 times 3x squared minus 1. Or that's not going to work. No, we can just do it both ways. Oh wait, what am I talking about, dude? We don't even need to do any of this. Okay, yeah, we don't even need to do this. What we can do is we can just factor the, so the x's cancel, and then we get x times x plus 1, x minus 1, divided by, and then let's just double check our work. Okay, so the denominator, denom, has 0 at x equal to plus or minus 1 over root 3, and numerator has 0 and plus and minus 1. Okay, so we found the roots. So we found the roots of the Newton iteration. So we can find the fixed. So we have the fixed points, right? Now we need to take the derivative. We need to take the derivative of the Newton iteration. And the derivative of the Newton iteration is going to be the derivative, it's going to be 1 minus the whole polynomial x cubed minus x divided by 3x squared minus 1 prime. Okay, so what we need to do, d of x cubed minus x divided by 3x squared minus 1 with respect to x. Okay, so this should be f prime. So now we should be able to do f prime, replace x goes to its fixed point, or it goes to f's fixed points, which are going to be 0, 1, and minus 1. So they're all 1. Is this right? And so that means that they're all neutral. So I'm guessing that they're all neutral fixed points. That seems unlikely, though. I feel like maybe it's more likely I did something wrong. Bum bum ba-dum ba-da-dum bum ba-da-da-da-dum da-dum do-do-do-do-do-do-do-do-do. All right, so we got this. And then what happened here? How did this happen? So okay, wait, hold on. So we got x times 3x squared minus 1 divided by 3x squared minus 1. And we got 3x cubed minus x. So then, okay, so then that equals 2x cubed over 3x squared plus minus 1. Wait, hold on. Did I do something wrong? You're not trying to find zeros for this, though. That doesn't make any sense. You're not trying to find zeros for this. A fixed points to the oh. Okay, yeah. So they got the same one. You really didn't need to do this step, but that's fine. All right, then we compute g prime, and we get, okay, cool. And then you evaluate it, and I think you do actually need x minus. Yeah, you do need that. Okay. Okay, so if there's 0, then they're all attracting. So it's just an algebra mistake. Okay, great. We can move on to, so I'm going to write that up in types later, but let's move on to 8.3, because 8.3 we need to do problem 10, I believe. So this is going to be 8.3 DE. And then we need to do 8.3 number 10. All right. Okay, 8.3, bifurcations. Just as with differential equations, discrete dynamical systems may undergo changes in their orbit structure as parameters vary. These changes may include the birth or death of fixed points and cycles, or changes in the type of these orbits. Actually, you know what? I want to have a little fun here. I just learned about classifying cycles as attracting, repelling, and neutral by if n period x1, x0, x1, x n minus 1, then we can look at f to the n prime and look at of x0 less than 1 and call the cycle. Okay. I'm curious for an example of a neutral cycle which is attracting on one side and repelling on the other. Does that make sense? Yeah, half stable. Right, because the thing is, because there's the other type of neutral fix, or wait. No, but I want a cycle. But I'm looking for a cycle that's half stable. Let's just give it the classification of periodic points. Or I guess I'm looking for not, well, how do you say it? We can look into this later. I want to do that at some point because that's really interesting to me. But we got stuff to do, bro. All right, bifurcations. Tangent bifurcation. One of the simplest types of bifurcation occurs when fixed or periodic points suddenly appear or disappear. As an example, consider the family of quadratic functions tangent bifurcation. Consider f of f sub c of x is equal to x squared plus c. And then we get fixed points of solutions to x squared plus c equals x. So x squared minus x plus c is equal to 0. And we get fixed points p plus minus the 1 plus or minus the square root of 1 minus 4c over 2. These fixed points are real. So c has to be, okay, so for real roots, c is less than or equal to 1/4. Ah, yes. I like the graphical approach. Oh, cool. The tangent bifurcation is, so you get this half stable thing. And then here, what do you get? You get, oh, and here you get a repeller. You get, oh, that's so beautiful. Wait, what did they do? So to determine the character of these fixed points, okay, yeah, so you just, oh, yeah, okay. Now if square root 1 minus 4c greater than 0. All right, anyways, they find that c is greater than, therefore for any fixed point p minus is attracting I like the graphical view so much more. Okay, as with differential equations, a picture is a useful way to display the changes that occur in a bifurcation. Figure 8.29 shows the bifurcation diagram corresponding to the bifurcation above. In this picture, the fixed points P plus and minus are plotted as functions of C. Ah, yes, okay. The perimeter C is plotted on the horizontal axis, and the x values of the fixed points are plotted. As C decreases through 1/4, that immediately splits into a pair of fixed points, one attracting and one repelling. Any bifurcation of fixed points or cycles that proceeds in this manner is called a tangent or a saddle node. Okay, I'll be back in a minute. What are you talking about? I spend like 90% of the time reading the textbook. Maybe like 75. All right. The fixed point structure of a discrete dynamical system may change in other ways. For example, consider the family of functions x cubed minus alpha x. So let's okay, so what's going to happen here is, like, for this, we're going to get a single fixed point of our system. And then at some point, what's going to happen? I mean, we get from 1 to 3, but there should be no intermediate 2. So you just instantly go from, is that true? From 1 fixed point to 3 fixed points. For a less than or equal to minus 1, we only have 1 fixed point. But when alpha is greater than minus 1, then there are 3. Hence okay. Yeah. Okay, so our saddle node, is like this. And then our pitchfork is going to be the classic pitchfork. So what does this mean? This means that for a given value of alpha, we can know how many fixed points we have. But I want the picture of the orbits. Okay, I guess they don't have those. But these pictures are even more insightful. I guess what we can do is we can kind of think about it in this way. So let's say we start here, or let's say we start like right here at this point. then we're going to go to here, and then we cross over to here, but then we go down here. So maybe this is attracting. We need to take the derivative to find out, and then these are repelling. Let's see, if we go here, if we start here, we go there, or if we start here, we go way down here, and then we go there. So this is definitely repelling on this side, but I think it's also going to be, yeah, we need to look at the slope. But if you're right here, you go up here, and then you go there, and then you go there, you go there. So this is attracting, and then so we have what happens at let's see, does this happen at 0? I think it happens when, no, it's a -1. So -1 is when this bifurcation occurs. And if it's less than -1, we only have one real solution. And what's going to happen is, let's say we start here. So the slope is greater than 1, right? So what happens is, since the slope is, or the absolute value of the slope of this graph is greater than 1, this is repelling. So what happens in the pitchfork here is that we have like a repeller that turns into a tuple of repeller, attract, repel. So that's what happens as we increase A. Boom. So this becomes an attractor. Okay, I'll be back in a second. All right, so let's get back into bifurcations, which might be my favorite section. All right, the pitchfork bifurcation rules. So I'm actually doing an interpretive dance degree. I'm a dance major. All right, so we understand the pitchfork bifurcation. Now this one is apparently, this one's the craziest one. Period doubling bifurcation. One of the most important types of bifurcations for discrete dynamical systems is the period doubling bifurcation. This bifurcation This bifurcation produces a new cycle having twice the period of the original cycle. For example, consider again the family x squared plus c. Recall this function has two fixed points. The fixed point p minus is attracting if c so we get 2x here for the derivative, and then we plug 2 into that, and then we see whether or not this is greater than or less than 1. So we plug this into the derivative of that. The fact that f prime p minus equal to minus 1 at c equals minus 3/4 is our signal, right, because it's minus 1, that a bifurcation may occur. Graphical analysis gives us a hint about what happens. In figure 8.31, we display the web diagrams. Note that the orbits tend to the attracting fixed point, but they tend to an attracting cycle of period 2. Okay, all right, believable. To find cycles of period 2 for fc, we must solve the equation f2 of x equal to x. Okay, we get a quartic. This equation looks tough to solve. However, recall that for any fixed point, fc must also solve the equation. That any fixed point for fc must also solve this equation. Is that true? If you have f of x equal to x, then f of x is equal to, yeah, okay, that's easy, that's true. So if for x0, fc of x0 equal to x0, certainly, okay, but we know that the fixed points, already of f. Okay, but let's take a step back. What are we trying to do? So they start off, they're like, hey, when we changed c, we found this value for c where we have a 2 cycle. And we're trying to find other 2 cycles, I guess. Anyways, we do the long division and we find, therefore, to find the cycles of period 2, we need to solve the quadratic equation, and we get these roots. Note that q plus minus are real numbers only if c is less than minus 3/4. Thus, a cycle of period 2 appears precisely when c decreases through minus 3/4. Any bifurcation in which a given cycle changes from attracting to repelling with the derivative passing through -1 and that is accompanied by the birth of a new cycle having twice the original period, called a period doubling bifurcation. This is a differential equations book. This is a hard one to get. Any bifurcation in which a given cycle changes from attracting to repelling with the derivative passing through -1 and that is accompanied by the birth of a new cycle having twice the original period is called a period doubling bifurcation. A qualitative view of this period doubling bifurcation is provided by the graphs of the second iterate of So actually, if we took, what was it, x squared minus c? Or was it x squared plus c? It was x squared plus c. So if we did x squared plus a, and then we did, I think we can do f of x. How do you define functions? What? How do you define a function? Oh, I think you can just do that. So if we just did f of x is equal to x squared plus a, then we just did f of x. What does that give me? Does that give me what I want? All right, let's just do it the slow way. So we have x plus a, and then we have this squared plus a. Qualitative view of this period doubling bifurcation is provided by the graphs of the second iterate of f of c. So how do we know that a cycle appears? Note how the graph twists through the diagonal to produce a pair of new fixed points. So I understand that. So F2, so in a way, F2 undergoes a pitchfork, right? F2 goes to pitchfork. But so, okay, so the fixed points of F2, not all of them are going to be 2 cycles, right? But these guys are. But how do we know that? I don't know how we know that, but I think they are. But this guy is still our original one, and that shouldn't move. I don't think that ever moves. Oh, wait, does it move? Oh, it does move. Oh, yeah, it moves, but this is maybe the better picture, is that it doesn't, yeah. Okay. I kind of get it. I don't know. This is going to take some more thought. That's definitely the hardest conceptual one. All right, the types of bifurcations discussed in this section are just the beginning of a long story of how discrete dynamical systems evolve as parameters are varied. To illustrate this in a concrete setting, we return to the logistic family of functions given by Lk equals kx 1 minus x. Recall that x represents the fraction of the maximum possible population, so we only consider 0 to 1. We use a combination of qualitative, analytic, and numerical methods to analyze this family of functions. However, the fate of orbits for many parameter values in this system is still an unsolved problem. So we are not able to describe completely what happens for every parameter value in seed. The first step in analyzing this family of functions is to find the fixed points. Okay, we get 0 and k minus 1 over k. That's just by solving this equal to x. Note that pk lies in the interval from 0 to 1 only if k is greater than 1. Otherwise, p is negative and is not of interest as a population model. Differentiating Lk, we get k times 1 minus 2x. Hence, L prime of k at 0 is equal to k. So we conclude that 0 is an attracting fixed point for 0 to 1 and repelling if k is greater than 1. Graphical iteration gives us much more information. Cool. That's nice. I like that. What type of bifurcation is that? What is that called? We have 3 types. We have tangent, pitchfork, and period doubling. For the other point, we conclude that okay, and we find that therefore pk is attracting. So is there another graph? What happens when you keep increasing it? PK is attracting for K in between 1 to 3. Again, using graphical iteration, we see from 34 that all seeds between 0 and 1 have orbits that tend to this attracting fixed point. In terms of populations, we conclude that when K is between 1 and 3, the population of our species eventually levels off at the constant value K minus 1 over K. If K is equal to 3, L prime is equal to minus 1. So it's a neutral. And if it's less than if it's less than minus 1, yeah, it's going to repel. Note that these orbits tend to the attracting fixed point when K equals 2.8, but to a 2 cycle when K equals 3.2. In terms of populations, when K is slightly larger than 3, we expect the populations will eventually cycle in a biennial cycle. 1 year it's high, the other year is low. Bro, here's this section of the frickin' ages, man. The period doubling route to chaos. It is impossible to use analytic methods to describe much of what occurs for the logistic family as K continues to increase. So we resort to qualitative and numerical methods. For the remainder of this section, we give only a glimpse of the very complicated mathematics that arises. Figure 36 provides a movie of the graph of LK for 6 K values between 1 and 4. As K increases, note how the slope of the tangent line to the graph of LK at PK decreases, eventually passing through the period doubling point at which the slope is minus 1. So the slope at this point of the graph. And the slope at that graph, when it's less than minus 1, it becomes a repelling fixed point. Figure 37 provides another movie, this time of the graphs of L2 for 6 other K values. Small boxes superimposed on each of these graphs are not web diagrams. Rather, they are intended to draw your attention to the piece of the graph of L2 inside each box. Note that these graphs look exactly like the graphs of LK, only smaller and upside down. Bro, this stuff gets really complicated, yeah. As we watch K change, we see these small pieces of the graph of L2 behave just as the graphs of LK do. Hence, we expect L2 to undergo the exact same bifurcations that LK did. Wait, actually, hold on. So if we go back up to here, so we have one. Okay, so let's say we know F has a fixed point. Has one fixed point. Then we vary C while looking at F2. If F2 had only one fixed point, then 2 showed up, must they be 2 cycles of F? I think so. I think that's what they mean by period doubling, is that these new ones have to be 2 cycles of F, because they're not fixed points of F. We know that they're not fixed points of F because we said F only has one fixed point and it stayed here. So then if we just get like this, or I guess in this case, let's do the logistic one. Instead of this, let's do the logistic one. So we're going to get AX 1 minus X. And then we're going to then we should get A of this. Wait, hold on. Can we just do this with a real program? So if we have f of x is defined as AX times 1 minus x. Then we just do f of x. Oh, wait. And we get a squared 1 minus x. I wonder if I can not have it simplify. It doesn't matter. 1 minus a, 1 minus x, x. A squared 1 minus x, x. Oh, yeah, no. A squared 1 minus x times x. Yes, it's going to be a times x, ax 1 minus x times 1 minus ax 1 minus x. Okay. All right, that's just what it is. So let's plot it. So we have, so it's going to be a times this times 1 minus this. Okay, cool. So now, it's kind of hard to see, but okay, so we want these values. There we go. There we go, baby. All right, so let's drop it down. So we have, so this is f, and we have 2 fixed points. But then as we increase this thing, so that means that, and this is also a fixed point of this by necessity, just because, like, wait, we did show it, but now I'm blanking. If f of x equal to x, then f of x is equal to x. Yeah, okay, that's fine. Okay, and so these are fixed points of the iterate. So but they're not. So those are fixed points of f2, but they're not fixed points of f. Therefore, they must be 2 cycles, right? So if I have f that has one fixed, or let's say one fixed point, and depends on some parameter, and I look at the iterate f2 equal to x equal to x, or let's say I have f of x that is one fixed point and depends on some parameter, and I look at the iterate and where they cross the y equal to x line, for then as I vary the parameter, I see that new roots show up on the intersection of y equal to x and f2 of x. Since these are not fixed points of f, then then they must be 2 cycles of f, right? I'm almost positive that's the case. Dude, the craziest thing is thinking about the fixed points as 1 cycles. That's the coolest part, man. Okay, so I like vaguely get the period doubling bifurcation. I'm not going to say I understand it, but it's sinking in. Dun, 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 dun. Okay. All right, let's read this. To make this precise, note that there is a fixed point for L2. This is actually a fixed point for LK and not a periodic point of period 2. As K increases, we see the birth of a new fixed point for L2. This point lies on a cycle of period 2 for L. Call this QK. The point QK is at first attracting, then repelling, as the derivative passes through -1. at first attracting then repelling as the derivative crosses -1. The derivative of L2 at QK, the derivative of L2, right, crosses -1. Oh, yeah, right there and right there. So if we took this and then we did A times this times 1 minus this, wait, but that's L3, isn't it? That's L3, not L4. Oh, man. Another way to view this would be to draw the graphs of L4 over the intervals of X contained in each of the small boxes. If we do this, we see that the graphs of L4 resemble the corresponding graphs of L2, only much smaller and turned upside down. We magnify those pictures and turn them around. We see that the pieces of the graphs of L2 and L4 look exactly like those of L. So we got a fractal. We got a fractal, baby. The process of iterating and zooming into small portions of a graph is called renormalization. Borrowed from physics, this process allows us to recognize certain patterns that occur over and over again. For example, we could now renormalize the graph of L4. We would see that over a smaller interval of k values, the 4-cycle discussed above would itself undergo a period doubling bifurcation. That is, the attracting 4-cycle would become repelling, and a new attracting 8-cycle would be born. This scenario continues with the successive births of 16, 32, 64. This phenomenon has been called the period doubling route to chaos. Bro, that's crazy, man. As the parameter k continues to increase, we eventually leave the period doubling interval and encounter a new type of behavior, chaos. For large k, the logistic family exhibits the type of behavior shown by the case 3.9. While we cannot fully explain what is happening to orbits for values in this regime, we can describe some simplified models of this chaotic behavior. Okay, so now we need to do problem 10, and then we'll type them up, and then we'll be on our way. I'll be right back. All right. Show explicitly that there exists a cycle of period 2 for k greater than 3. Okay, so first off, let's find the 1 cycles of f. Wait, hold on. Let's see. Let's think about this, because sometimes you can read a section and you really need to let it seep in. So to show there exists a cycle, so first off, if we find so the first thing we're going to do is figure out where this point is, right? Because this point and this point, which are the fixed points of the logistic map. So we get kx minus kx squared equal to x. So then we get how do we solve this? Minus k x squared plus k minus 1 times x is equal to 0. We can move it to the other side and we get we get x is equal to 1 minus k. Wait, I think I did it wrong. One minus k. Where did that minus sign come from? Yeah, there's a minus sign there. Oh, but this is going to be minus k minus 1 x minus kx squared divide. All right, so yeah, we get x is equal to k minus 1 over k and 0. So these are the fixed points of LK. Now we're trying to show that there exists explicitly, and where did they mention it? They mention in exercise 10, we asked you to verify this. Okay, so now that we have the fixed points of LK, what are we trying to show? We're trying to show that okay, so let's just do what we've learned and then see what sticks. I actually like that strategy. So what do we know how to do? We know how to take f prime. So f of x is equal to kx 1 minus x, which is equal to kx minus kx squared. And f prime of x is going to be equal to k minus 2kx, which is equal to k times 1 minus 2x. Okay, so they had that up above. Now, what we want to do is feed in the fixed points that we found to this, this L prime function. And when we do that, we will see whether it's attracting or repelling. Okay? So we get f prime of k minus 1 over k. If we do the 0 case, this just becomes k. So f prime of 0 equals k times 1 minus 0, which is equal to k. All right, so in that case, we know that it's going to be repelling for the absolute value of k greater than 1 and attracting otherwise. Or not otherwise, but for absolute value of k less than 1. Because when it's exactly 1, it's something else. I should have set my camera up today, but I didn't. Okay. I do have a new microphone, though, guys. If my audio quality sounds good, it's not a coincidence. Okay, so then, all right, so let's plug in f prime of k minus 1 over k. So we're going to get this thing, right? We're going to get k times 1 minus 2x, which is going to be k minus 1 over k. So that's going to be 2k minus 2 over k. 1 minus times k. We get k minus 2k minus 2, which should be equal to this becomes a plus, a minus, a plus. So then we're going to get, k minus 2k plus 2, which is equal to minus k plus 2. Okay. So then, basically, for that second fixed point, so for this one, which is kind of the one of interest, when the absolute value of minus k plus 2 is less than 1, so for 1 to 3 is the zone for attraction. Okay, so we're just rederiving basically all this stuff that they did in the book to figure out that this is the attracting zone. If k equals 3, then we have a neutral or whatever. Right. And if k is greater than, thus changes from attracting to repelling, and we expect a period doubling bifurcation. I never really understood the proof of that. The way that I would show, because what is it that our problem is telling us to do? It's to specifically, wait, we went too far. It's show explicitly that there exists a cycle of period 2 for k greater than 3 for LK, for the logistic map with parameter k. So the way that I would show it, though, is I would take the iterate, so I would take F2, so I'd iterate this thing one time. Then I would factor out the pk root, which is the root we just found, which is k minus 1 over k. And then I would solve that inner quadratic equation, and that will give me something that depends on k, that tells me what the two new roots of F2 are. Then we show that the point at which those emerge, in which that discriminant is not 0, is when k is greater than 3. So that's how I am going to attack this problem. Okay, so let's just do it on here. So we have F, so we have the logistic, and then, so let's call this so what do we want to do? We just want to take, here, we can just do this. So we have F and F2. Now we want to show all right, so here are our roots there. Now what we want to do is we want to solve the quartic. So if we just do F2 of x, what do we get? We get this quartic equation. Okay, so we have this one, but then we have these two new ones, right? And the point is we want to look at this discriminant, which is going to be, I'll call it d of x is equal to minus 3 minus 2x plus x squared. We want to solve d of x equal to 0 for x. And we're going to get minus 1, which doesn't make sense for our parameter. Wait, does it? No, it does. That actually does make sense, because that is going to be the other side of it. That's going to be the other side of that k, because we said that k has to be, what did we say? We said k is attracting between, oh wait. No, what is this minus 1 about? When a is minus 1, okay, but this is my proof, is that we are going to get Oh, but you know what? This is when it goes negative, I think, right? Because if we plug in d of minus 1.1 or something like that. No, it's positive. Can we do this? Can we give it a list? Oh, you know what? Okay, so it's... Yeah. I think so. Wait, hold on. Sometimes you think you got it and then you don't got it. I don't know. When k is... Okay, so we've already proven that when k is between, in this case a, we're calling it a here, but it's the parameter. When the parameter is between 1 and 3, it's attracting. So actually what we could do is we could say f2p is equal to f2 prime of x. Actually, we probably want to do like this, right? Oh, shit. Yeah, we have to... So wait. Let's just take stock, because this problem is pretty complicated. Here's the steps that we took. So first we took LK, or FK, whatever it is. We took this, then we set it equal to X to find the fixed points of the logistic equation. And we found 2. We found 0 and k minus 1 over k. Then, to determine the stability of those fixed points, we took f prime and plugged in our fixed points into the derivative. Now, why does that give us the stability? What happens if we're out of here and it's negative? So this is negative, so this is going to go here to a negative. And this is going to go down. And this is going to repel away. No, wait, that doesn't sound right. Okay, wait, we can easily check the orbit of this. So this is for 2.8. So if we take Lx is defined as 2.8x times 1 minus x. Then we do nest list of L, and then let's see, what is the documentation of this nest list thing? Okay, then we give it just, let's say like 2, and then 10 iterations. So it goes negative, and then it goes, because this thing is repelling. Where's our diagram? Because this one is repelling. So, but this is supposed to be attracting. But, okay, wait, hold on. If we do it from like here, like if we did it from like 0.9, this is, so we're going to have 2.8 minus 1 over 2.8. It's like 0.6, right? Yeah, so if we did this like 30 times, we get something really close to it. So it's not like globally attracting. It's locally attracting, right? It goes to infinity, or where does it go? To minus infinity. I think that's correct. I think it's just because it's a local attractor. Right, we just have some interval, but we don't know what interval. Okay. Okay, so where are we at with this? We D, this is positive. So that means that we are going to have these two solutions are real. Because they're where they're at right now, here at this cell, they're not necessarily real. But for value 3.1, we see that we have a real value of the discriminant, or positive value of the discriminant. Therefore, two real solutions to x. Okay, so if I were to write this up, I would say, show explicitly first, so for 10, first we show okay, so here's what I would say. First, we show the fixed points of fk. Then we take f2k and factor out the fixed points of f. Then we are left with a quadratic that has a zero discriminant when x, or when k equals -1 and 3, and it is real valued for k less than -1 and k greater than 3. Since k greater than 3 gains 2 real roots for the polynomial f2k, then and these are not the roots, are not the fixed points, or wait, sorry. Since k greater than 3, fixed point of f2k gains 2 real roots, and these are not the fixed points of fk, then they must be 2 cycles of f. Okay, that's how I would answer it. But I don't actually know if that's the best way to do it. That looks like what it's thinking about. But sometimes it's thinking about nonsense, and then it gives you something totally different. So we will see. All right, so let's see. Here's the usual by hand derivation. We look for points of exact period 2, i.e. solutions to f2 equals x. which are not fixed points. Okay, this is exactly what I was thinking. This is the cleanest way for me to do it. I don't know what they were saying about like, oh, it goes from -1 to, or from less than -1 to greater than -1. That's not, I don't know. That didn't really do it for me. Okay, so we get this polynomial. Then we write down this. Okay, so then they find the then they find the fixed points of fk. Therefore, the equation has 3 real roots. Oh, wait. Wait. This is 4. Okay, so but anyways, the point still stands that we have 2 new ones that are not fixed points of fk. Therefore, they have to be fixed points of, they have to be 2 cycles of f. You perform polynomial division. So this is what is this? And what is this? What is that? Right now it's not linear algebra. It's differential equations. And what might this be? Where is this coming from? I mean, this is the part that matters. K equal to 3 and k equal to -1. That's really all you need. Because then you show, well, you need that, and then you need to show that when k is greater than 3, this thing is positive. Okay, wait, I'll be back in a second. Why do we require k greater than 0? Why can't k be negative? Okay, this is what I wanted to know. How do you factor out the... Count them up. Right, yeah. Okay, so we need to actually derive, though, because what did we get? We got this. We got this. So just say this is f2x. If we factor f2x, we have an x. Wait, where does this 3 come from? Because if we have ax squared minus ax plus 1 equal to 0, right? Then we're going to get a plus or minus the square root of a squared minus 4a over 2. Or over 2a, right? Minus b squared plus or minus, or minus b plus or minus square root of b squared minus 4ac over 2a. So then we get 2a here. So then a times a minus 4. I did not do this factoring right. How did they get this? How did So we're up to here. This all makes sense. But then you factor off the fixed points of fk. The fixed points of fk are 0 and k minus 1 over k. We did that. Therefore, okay, yes, we got this, right? This is just f2. Then we perform... Then f2 minus x, which is finding the fixed points, is equal to this minus x. So then we get though we factor out this x. That's fine. Notice the non-zero fixed point of fk is also a root. Yes. Since any fixed point... Oh, wait. Since any fixed point fk must also solve the linear factor... Okay, since f of k minus 1 over k is equal to x, then f2 of k minus 1 over k is equal to x. So that's just for sure. We know that. That's not a big deal. But let's just do the expansion of that then. Or is that a lot? Oh, okay. So then we write. Wait. So we took out the first root. Now we're trying to take out the second root. And the second root ask you to simplify it. Oh, wait. So we have the polynomial. Okay, hold on. Yes. Okay. Very good. Yes, the linear factor. Okay, this makes sense. All right, so I think we're ready to actually type up our answers, right? Let's type it up. Type it. DE extra credit. Do 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 do. Dude, how good is New Jabez? Dude is fucking awesome. Oh, wait, let's just delete all of this crap. This is going to be 8 point... Oh, but you know what? We're actually not done. We can do the problems, but we actually have to read 8.4 and 8.5 because we need to compare and contrast, I think, these two figures. Let me check. I think we have to compare and contrast 49 and 50. Yeah, so we need to compare and contrast. And I don't even know what this means, so we're going to have to keep reading. All right, but let's type up our two answers maybe. Because we have 2 more sections to read. This is going to take forever. But actually, it looks really interesting. So this is going to be 8.2 and 8.3. Oh, the way I wrote this is for a single section, single... so we actually need like a... Oh, we need a trailing comma here. 1. 2 prob stir, we do... It takes a... So... 2 prob stir. 2 homework. Instead, we're going to do... this. Is there a splat operation? Can I splat it? I don't know how we want to do this. Maybe I'll just not... Maybe I'll just forgo this template thing and just write it as I want to. I think we can do that. Let's just do that. So... where is... can we do heterogeneous types? I can just put this here. It's going to be, so wait, what's the title? So 8, wait, hold on, where is this thing? Oh, you know what? No, what? Okay, let's just, what if we do this? For, do they have a formatter? All right, I don't know why I care. Let's just, let's just, let's just put the number here. Okay, then we just like don't even do this. All right, so just get rid of that. So prob. Oh yeah. Let's just not do this, right? Yeah, let's just do that. Okay, that's fine. So we'll have 8.2 number 30. All right, now that we have the formatting figured out, let's go read the problem again. 8.2 number 30. I remember this one is pretty easy. Okay, so let's do the following. Let Newton equal the formula, so this is going to be x p prime pp is equal to this should be a function, right? But is that going to actually work? Yeah, what are we doing? We gotta hurry up. We really do. Okay, so let's just do this the simple way. So we're gonna have x oh. Okay, so what's the problem? Show that a root of p. Okay, so is a fixed point of the Newton iteration. Okay, so So wait, what is the question? The question is, show that a root, okay, so 8.230 DE 30. Show P of x is equal to 0, P prime of x not equal to 0 is a fixed point of Newton. Okay, so fixed points of this iterative function, this function, are x equal to Newton of x. We can cancel the x on both sides to get p of x divided by p prime of x. The problem tells us that p of x is equal to 0. Zeros of the expression we assume p prime of x. Therefore, our fixed point expression becomes 0 is equal to 0 divided by non-zero equal to 0. Therefore, x is a fixed x where p of x equal to 0, p prime of x not equal to 0 is a fixed point of the Newton. What do they call it? Okay, now we want to show p of x is equal to x cubed minus x, right? Determine whether the fixed points correspond. Okay, now part B, x is equal to x cubed minus x. Okay, so how long have we been going? 3 hours? It's not even that long, man. The problem is what? Is Since I don't trust my own garbage code, I have to write this by hand, but I really need to fix my code. Oh, wait. Wait, hold on. We have our Newton iteration, x is equal to x minus p over p prime. Then we get p over p prime is equal to 0. And then we just take the derivative of both sides. So actually, it just needs to be this. Oh, wait, are we supposed to compute no, so the function f is, okay, I get it. So the function f is, or wait, so we can actually just say f prime, where f so we compute the derivative, and the derivative is six x times x cubed minus x divided by 3x squared minus 1 squared. We can factor the numerator into x minus 1, or let's do, so wait, can we just take foo All right, cool. So we did one problem, and that's problem 30. Yes, yes, yes. P figs, tan, and P figs. Okay, problem 10 is way harder. So let's look at problem 10 again. I think the first part is easy, but oh no, this is just hard because, okay. Well, let me just write out what I had on paper, and then we'll use that as a guide. Okay. So this is going to be 8.3, number 10, or 10. Let's okay. KX. Oops. We're getting there, but I'm getting kind of hungry, man. All right. So wait. So let's just finish this. Well, we have to do. The figures. All right. Let's come back to writing this. We have most of it done, I would say. We just need to write a bunch of symbols down. But let's just briefly go through the section that's on chaos. You know, I'm going to make some food. Let's see. Nah, okay. In this section, we begin the study of chaotic behavior. Until a few years ago, most scientists and mathematicians thought that typical differential and difference equations did not exhibit the kind of behavior that we now call chaos. This kind of behavior was extremely unlikely in simple mathematical models. Now we know this is not the case. There are many models whose behavior is quite erratic, and this behavior persists when parameters are varied. Moreover, mathematicians have begun to develop techniques to predict the onset of chaos and to determine the scope or limits of this behavior. In this chapter, we use a number of qualitative and numerical techniques to explain and illustrate the concept of chaos. An example without chaos. Roughly speaking, chaos means unpredictability. Thus far, most of the differential and difference equations we've encountered have been completely predictable. For example, consider as we've seen, this system has two fixed points. Graphical analysis shows that the orbit of any seed x0 in the interval from 0 to 1 tends to 1/2. The only other point, x0 equal to 1, has an orbit that is eventually fixed. So we know the fate of all orbits. Right, because 1 goes down to here and then across to 0. Now, in real life, we rarely know the seed for our orbit with complete accuracy. For example, we most likely do not know the precise value of the population at time 0. We probably miss a few individuals in our initial count. If our model is the simple logistic model above, however, this inaccuracy does not really matter. A small fluctuation in our initial seed does not alter our predictions at all, because it always just goes to this 1/2 point, or 0, if it's at 0, or 1. All right, a chaotic logistic function. Now let's contrast the orbits of the logistic model above with those of where we changed 2 for 4, where we have simply changed the growth parameter from 2 to 4. As always, studying this system is the same as iterating the function L4. This function has fixed points 0 and 3/4, and eventually fixed if we have 1/2, then this goes to 2, and this goes to 1/2. So 2 times 1/2 is 1. So eventually fixed points. So these points eventually become fixed. But consider the fate of virtually any other orbit. We compute the web diagram for the first 200 points of the orbit of 0.123 for this function. It is hard to distinguish any pattern in this picture. A histogram and a time series for this orbit confirm this erratic behavior. In the histogram, we see that the orbit seems to visit every small subinterval many times. If you repeat this experiment for a variety of seeds, you will see essentially the same results in each case. Of course, the fixed points and eventually fixed points yield quite different diagrams. However, virtually any other seed yields figures that resemble those of these. So you can't tell what the heck is going on. Okay, so we made this here. These computer experiments suggest that most orbits of L4 behave erratically. However, there are many cycles for L4 as well. In figure, we plot the graphs of L2, L3, and L4 of 4. Note that the graph of Ln appears to cross the diagonal at 2n points, or 2 to the n points. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Wow. Yielding infinitely many cycles of arbitrarily high period in the interval from 0 to 1. That's psycho. Arbitrarily high, but we don't have any period that we want, right? Like, these are all periods of powers of 2. Another important element in our discussion of chaotic behavior is sensitive dependence on initial conditions. This is illustrated where we plot the time series for the orbits barely different. These orbits seem very close initially, but then they totally change. Just after a few iterations, the orbits separate and bear little resemblance to each other. A model chaotic system. To characterize the chaotic behavior we observe for the logistic function, we turn to a discrete dynamical system that is much easier to understand. Consider the function t defined from 10x mod 1. Oh shoot, I've never seen this function before. This is wild. Yo, that's crazy, dude. That reminds me of like... Yo, that's crazy, bro. What the hell? Oh, dude, the chopping function, bro. I love it. I love it. I love it. I love it. The chopping function is sick. That's so cool. Oh, the chopping function, dude. Yo, all my homies love the chopping function. Damn. Not the chopping function, bro. All right, density of periodic orbits. Because of the special definition of the chopping function, periodic points of t are easy to find. Any x whose decimal expansion is repeating lies on a cycle for t. 2 to the 9 is a fixed point. Similarly, 0.37 lies on a 2-cycle, 4-cycle. Yeah, exactly, bro. We can just make whatever we want, dude. Bro, the chopping function. Moreover, unlike the logistic functions, we can write down all of the periodic points for t explicitly. I know, dude. That's the sickest part about it. Because like I was wondering, I was like, what? But yeah, we can make weird functions. Bro, fan of the chopping function? I am. There's more to this story, however. Given any x in the interval, we can find a periodic point of t arbitrarily close to x. Oh, dude, whoa. That's actually crazy. Yeah, we can find a periodic, but it's easy. That's the thing. It's like, this is such a good example. There's more to this story, however. Given any x in the interval from 0 to 1, we can find a periodic point of t arbitrarily close to x. This follows since if x is the decimal expansion, you just take all, as many as you want, and you just make it repeat. And you have a periodic trajectory that's as close as you want it. That's crazy town, bro. If you guys don't think that's crazy, man, I don't know what's going to blow your mind. For example, suppose we're given the number 1 over root x, or root 2. We are asked to find a periodic point within 0.001 units of x. We could choose 707 repeating and excess period 3. But there are many other choices that work as well, including something way more accuracy and even way more accuracy. So not only can you find well, actually, the funny thing is that you don't even have to repeat the whole thing. I guess you do because we're talking about periodic, but you can find something that's eventually periodic. You can make a number that's eventually periodic of any cycle length that's arbitrarily close to some other number. Extrapolating from this example, we see no matter how small a subinterval we choose, we can always find periodic points inside the subinterval. In fact, we can always find infinitely many distinct periodic points inside this subinterval. Wait, what does that mean? In fact, we can always find infinitely many distinct periodic points inside the subinterval. Yeah. Right. Yeah, of course. A subset of which contains points in every subinterval. A subset of the interval from 0 to 1, which contains points from in every subinterval, is it's called a dense subset. Yeah. For example, the set of all rational numbers is dense. So too are the irrationals. The above argument shows that the set of periodic orbits for T is a dense subset. Bro, that's what a beautiful thing to say. What a beautiful thing to say. So the set of periodic points of T is a dense subset of 0 to 1. Beautiful. What a fun thing to say. This is like my favorite chapter. It's just so cool. You know? I need some water. I'm getting thirsty. Oh yeah, see, we just said this. This is eventually periodic with any period. Bro studying at Chopped University. Periodic orbits are by no means the only types of orbits. We have eventually periodic points as well. Any point whose decimal expansion eventually begins to repeat is eventually periodic. Similarly, the orbit, okay, now recall that any rational number has a decimal expansion that either repeats, eventually repeats, or terminates. Is that true? Did they prove that? I don't remember seeing that. That's crazy. Or a sequence with all zeros. As a consequence, we see that any rational number oh shit, okay, so wow, what a beautiful way to understand the rational numbers. Any rational number in 0 to 1 has an orbit under T that is either periodic or eventually periodic. Meaning fixed as well. On the other hand, any irrational number that, oh, wow. Yeah, man. What a fun way to understand numbers as a dynamical, as a difference equation. And irrationals, never periodic. Oh, dude, this section is actually the trippiest section. Y'all studying at Chopped University? I called them, said you were their top student. Oh, man. I called the administrators, bro. They said y'all are the top students at Chopped University. Bro. A dense orbit. Some of these irrational numbers have very interesting orbits. For example, consider the number x0 whose decimal expansion begins. Whoa. See, it's just like a fun way to think about a number. Suppose the next 200 terms of this expansion consist of all possible 2 blocks of digits, and then 3 blocks and 4 blocks and so on. What can we say about the orbit of x0? So is this an irrational number? It never repeats, right? Oh, yo, wait. This is like a cool way. Wait, let me think. I feel like it feels like one of those fancy tricks where you can show that the rationals are countable. We see that there's a point on the orbit of x0. Oh, wow. Dude, this is like the best number ever. What do they call this number? It's like the best number ever. I swear math is the trippiest subject, dude. We need only to iterate t enough times so that the first n digits of the decimal expansion of x appear as the leading terms of this point on the orbit. Wait, let's just remember what t is. T is the chopping function. Yeah. Wow. Of course, there are many other points on the orbit of x0 that lie within. All we need to do is iterate t enough times until any kth block. Yeah. Yo. Dense orbit. Bro, it sucks that they didn't teach this in our class, man, because this is like actually really wild. So you do 0.1, 2, 3, 4, 5, 6, 7, 8, 9. Then you do 0, 1, 0, 2, 9, 9, and 0, 0, 1. Or do you do 0, 0, 0? Maybe you do 0, 0, 0. I don't know, but you probably have to do 0, 0, 0. Yeah. You do 0, 0, 0. Okay. Sensitive dependence on initial conditions. The final observation we wish to make, is this the, are we almost out of here? We got, bro is the top student at Chopt University. I humbly accept this scholarship to Chopt University. All right, let's read this. The final observation we wish to make about T is that this dynamical system exhibits sensitive dependence on initial conditions. By this we mean the following. Consider any x0 then there are points y0 arbitrarily close to x0 so that the orbit is eventually far from that of x. For example, if you consider the fixed point x0 equals 1/9, then there are nearby points whose orbits behave very differently. For example, the seed repeated 1s and then eventually 8s eventually lands on the fixed point 8/9. How close y0 is to 1/9 depends on how many initial 1s are present in the sequence. Although these two seeds are close together initially, their orbits are eventually far apart in the interval. As another example, we can consider a seed that repeats eventually at 35, and then another one that repeats eventually at 2, 3, 4, 5, 6. Both of these seeds are close to x0, but their orbits behave quite differently. Indeed, arbitrarily close to the given seed, we can find another seed whose orbit eventually has any behavior whatsoever. All we need to do is precede it by a sufficiently long string of 1. Dude, these kind of arguments are just the best. This is why I like computer science. The general situation is familiar. Yeah. Okay. The existence of sensitive dependence in dynamical systems has profound implications for scientists and mathematicians who use difference or differential equations as mathematical models. If a given system exhibits sensitive dependence on initial conditions, then numerical predictions about the fate of orbits or solutions are to be totally distrusted. For we can never know the exact seed or initial condition of for our orbit, or solution, because we cannot make physical measurements with infinite precision. Even if we had exact measurements, we can never carry out the necessary computations. Throw small numerical errors away that are always introduced into such numerical procedures. Throw us off our original orbit and into another whose ultimate behavior may be radically different. Unlike T, for which we have sensitive dependence at all points in its domain, many functions exhibit sensitivity only at isolated points. Consider, for example, our logistic at 3.2. Most orbits tend to an attracting cycle of period 2. However, not all orbits share this fate. As we see in figure 45, there are two repelling fixed points. And there are infinitely many points whose orbits eventually land on the non-zero fixed point. these functions oh yeah, there are infinitely many. You just get really, really close to zero. That's crazy, man. That's like when you like throw a basketball from the other side of the world and then it goes in the hoop. Bro, the chopped fucking function, man. This behavior is much different from what we see. It's called unstable behavior. Chaos occurs when we have unstable behavior everywhere, or at least on a large set. We have shown that our model system T possesses an amazing amount of complexity. The periodic points of T form a dense subset of this interval, and there's also a single orbit that forms another dense subset of... That's what's crazy, man. Is that the orbit of the freaking... I'll call it the dope number. The dope num. Bro, the dope num's orbit is a dense subset. Moreover, this function exhibits sensitive dependence on initial conditions. Okay. It may seem that this type of complexity is special to our model function T because it has constant slope 10. However, over the past few years, mathematicians have verified that a number of dynamical systems, both discrete and differential equations, exhibit this type of behavior. For example, there's a large set of k values for which the logistic function is chaotic. The histograms gave qualitative evidence of this behavior. All right, so we're not doing anything here. We do need to read this, but I'm getting so hungry. Is there actually 6 people watching right now? Bro, y'all attend freaking Chopped University. I'm telling you right now, y'all are chopped. All right, so let's do chaos in the Lorentz system. Actually, you know what? Well, let's see, how long is this thing? Okay, it's not that long. We should just power through. All right. 8.5, chaos in the Lorentz system. In this section, we complete the discussion of the Lorentz system of differential equations. Recall that this system is a nonlinear system. We will first show how to reduce this problem into a two-dimensional model, and then we will further simplify the system into a one-dimensional iteration. Using techniques we developed in the last section, we will then show how this simplified Lorentz system exhibits chaotic behavior. All right, the Lorentz attractor. As we saw, virtually every solution curve of the Lorentz system eventually has similar behavior. After initially meandering around three-dimensional space, the solution curve eventually winds in a complicated fashion around a certain region in three-dimensional space. Our goal is to create a model of this behavior that will enable us to see more clearly how the solutions behave. For example, this figure shows the solution curve starting at the initial condition 0, 1, 0. After a short period of time, the solution settles down on a region where it winds around two holes in a seemingly random manner. The object toward which solutions of the Lorentz equation tend is called a strange attractor. Bro, whenever I hear the word strange attractor, I hear some trippy ass, I hear some crazy music playing because it's just one of the wildest things. But in a sense, it's too complicated. The chopped function is the best function. It is an attractor because all solutions tend to it. All solutions tend to it. But what is it? That's the question. What is it? It is strange since it's very different from the simpler attractors we have encountered thus far. Equilibrium points and certain periodic orbits. To understand this attractor, we will try to view it from many different vantage points. The easiest way to do this is to project the solution curve onto a coordinate plane. Geometrically, this means we simply forget one of the coordinates. For example, to project the xy plane, we just plot xy and then yz and xz. Note that each of these projections in the solution curve apparently crosses itself. By the uniqueness theorem, this does not happen in the full xyz space because it's, by the uniqueness theorem. So the real solution curve passes above or below itself in 3 dimensions. The advantage of projections is that they can be viewed on computer screens easily, whereas 3-dimensional images require some geometric intuition and perspective. The trick is to use various projections to piece together the behavior of solutions. Okay. The projections of the Lorentz attractor indicate that solution curves tend toward a region in the 3-dimensional space that resembles the surface drawn here. I've never seen this before. This image is called the Lorentz template, although it is sometimes called the Lorentz mask. Note that the 2 lobes of the template are joined along a straight line, with one lobe bending backward and the other forward. The attractor for the Lorentz system is actually a much more complicated object. It consists of infinitely many sheets packed tightly together in a complicated fashion. However, this template allows us to get a good idea of the mechanism that produces the chaotic behavior in the Lorentz system. What follows is not an exact description of the solutions of the equation, rather it should be viewed as a simplification of the full system. To understand the full phase portrait of the Lorentz system, recall from section 5.5 that there are 3 equilibrium points. I don't remember that. I haven't even done that section. Okay, the Lorentz system has 3 equilibrium points. There's a saddle with 1 positive and 2 negative eigenvalues at the origin. But what is that, the linearized eigensystem? Because, like, all right, give me a second. Yeah, it's the. Oh, but you know what? That's actually valid. Yo, they valid for that. They valid for that. For real. All right, I gotta make some food. I'm gonna end it here. 200 views. That's pretty good. Peace out.